The difference between centralized database systems and developing a DBMS, database management system, from scratch lies in their approach to data management, architecture, and implementation. Centralized database systems. 1. Definition. Centralized database system refers to a system where data is stored and managed in a single location or a single server. 2. Characteristics. Single point of control. All data operations, storage, retrieval, updates are managed from a central server or database. Consistency ensures that all users and applications access the same data, enforcing data consistency and integrity through standardized data models and rules. Scalability challenges may face scalability limitations as data volumes grow, as scaling typically involves upgrading hardware or migrating to more powerful servers. 3. Examples. Traditional relational database systems like Oracle Database, MySQL, Microsoft SQL Server when deployed in a single server configuration. Developing DBMS from scratch. 1. Definition. Developing DBMS from scratch refers to creating a custom-built database management system tailored to specific requirements, rather than using an off-the-shelf solution. 2. Characteristics. Customization allows developers to design database functionalities, data models, query languages, and optimization techniques from the ground up to meet specific needs. Complexity and effort requires significant time, resources, and expertise to develop and maintain a DBMS, including implementing data storage, indexing, transaction management, concurrency control, and query processing. Flexibility provides flexibility in choosing underlying technologies, data storage formats, and optimization strategies based on unique application requirements. 3. Examples. In specialized applications or research projects, developers might build a custom DBMS tailored to specific data handling needs or performance requirements that cannot be fully met by existing database systems. Key differences. Control and standardization. Centralized database systems offer standardized control over data management, ensuring consistency and simplifying administration. Developing a DBMS from scratch allows for customized control but requires more effort and expertise. Scalability. Centralized systems may face scalability challenges as data volumes increase, whereas a custom-built DBMS can theoretically be designed for specific scalability needs, but requires careful planning and implementation. Implementation complexity. Centralized systems benefit from established DBMS technologies and support, while developing a DBMS from scratch entails addressing all aspects of database management and optimizing performance from the ground up. Practical considerations. Use case suitability. Centralized database systems are suitable for most business applications due to their reliability, support, and established ecosystem. Developing a DBMS from scratch is typically reserved for specialized needs or research projects where custom solutions are justified. Maintenance and support. Centralized systems benefit from vendor support and community resources, while custom-built DBMS requires ongoing maintenance and updates to ensure reliability and security. Database systems are software for application independently describing, storing, and querying data. The management component called the Database Management System, DBMS, contains a query and data manipulation language for evaluating and editing the data and information. This component not only does serve the user interface, but also manages all access and editing permissions for users and applications. When deciding whether to use relational or non-relational technologies, pros and cons have to be considered carefully. In some use cases, it may even be ideal to combine different technologies. Modern hybrid DBMS approaches combine SQL with non-relational aspects, either by providing NoSQL features in relational databases or by exposing in SQL querying. Interface to non-relational databases. Back to MapReduce. MapReduce, which is a programming model for processing and generating large data sets with a parallel, distributed algorithm on a cluster, would typically use a variety of tools and frameworks. A parallel, distributed algorithm on a cluster refers to a method of processing large datasets across multiple computing nodes, machines, that are interconnected in a cluster. Here's a breakdown of the key components. 1. Parallelism. This refers to the ability to divide a task into smaller subtasks that can be executed simultaneously. In the context of a cluster, parallelism allows different parts of a dataset to be processed concurrently on different nodes. 2. Distributed computing. In a distributed system, computing tasks are spread across multiple nodes in a network. Each node typically has its own processing power and memory. Distributed computing allows for efficient utilization of resources and scalability. 3. Cluster. A cluster is a group of interconnected computers or nodes that work together to perform a task. In the context of data processing, clusters are often used to handle large datasets that would be impractical or inefficient to process on a single machine. 4. Programming model. MapReduce is a programming model that simplifies the development of parallel, distributed algorithms. It consists of two main phases, map and reduce. The map phase involves processing input data and emitting key-value pairs, while the reduce phase aggregates and summarizes the output of the map phase. 5. Frameworks and tools. Data engineers working with MapReduce typically use frameworks like Apache Hadoop, which provides a distributed file system, HDFS, for storage and MapReduce for processing. Other tools and frameworks include Apache Spark, which offers more advanced processing capabilities beyond MapReduce, Apache Hive for SQL-like queries, and Apache Kafka for real-time data streaming. In summary, a parallel, distributed algorithm on a cluster leverages the combined computing power of multiple machines to efficiently process large datasets. MapReduce and similar frameworks facilitate this by providing a structured approach to parallel processing and data handling across distributed environments. Distributed computing is fundamental to many real-life applications and software systems, enabling efficient resource utilization, scalability, and fault tolerance. Here are some examples across different domains. 1. Cloud computing platforms. Services like Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform, GCP, provide distributed computing capabilities. Users can deploy applications across multiple virtual machines, VMs, or containers distributed across data centers worldwide. This allows scaling resources up or down based on demand and ensures high availability. 2. Big data processing. Frameworks such as Apache Hadoop and Apache Spark are designed for distributed computing. They allow processing of large datasets across clusters of commodity servers. Hadoop's HDFS, Hadoop Distributed File System, distributes data across nodes, while Spark utilizes in-memory processing for faster analytics. 3. Content delivery networks. CDNs like Akamai and Cloudflare distribute content, web pages, videos, etc., across geographically dispersed servers. This reduces latency and improves load times by serving content from servers closer to users, leveraging distributed computing to handle requests efficiently.